Okay, let's look at the next part. Consider the following apparatus containing helium in both sides at 45 degrees Celsius. Initially, the valve is closed. And it gives us 2.00 atmospheres, 9.00 liters on this side, and then I have 3.00 atmospheres and 3.00 liters on this side. It's the same type of gas, so we don't have to worry about any reaction. So we're going to use Dalton's law, but it gets a little tricky because if I open that up, I'm changing the volume of the entire container. This is in a 3-liter container, but when I open the valve, it's going to go into a 9 plus 3, a 12-liter container. This is in a 9-liter container. When I open up the valve, it goes and flows out into a 12-liter container. So they're going to combine in a 12-liter container. So after the valve is open, the question is, what is the pressure of the helium gas? Now, it's really tempting to look at this and say, oh, it's just Dalton's law, 2.00 atmospheres plus 3.00 atmospheres. Well, that would make this 5.00 atmospheres. Sounds like a pretty reasonable thing to do, but let's think about what we're saying there. We're saying if I just turn the valve, then the pressure in that whole container is going to be more than what I started with. Now that sounds like some crazy magic trick to be able to do that, to take pressurized air at 3 atmospheres and 2 atmospheres, and you open a valve, and when they combine without a chemical reaction at all, the pressure just increases to 5. That's not realistic. The realistic situation is our pressure has to be between 2.00 and 3.00 atmospheres. That's more realistic. It's going to mix together to give us something between that. Well, how do we find the pressure? It's a challenging question. But what's changing? What are the only variables that change when I open this up? Well, the volume will change. We just talked about that. Is it possible that the pressure would change? Well, it sounds like it probably will. Okay, so what I want you to do is think about this as 2 separate problems where the pressure and volume change. We're going to find a new pressure for each container, and then we add them together. All right, so we're going to end up with container A on this side, and I've got container and gas B on this side, and we're going to solve individually for their new pressures, and then we're going to add them together. All right, so I've got for A, we're going to use, because we just said our pressure and our volume, we're going to use P1 V1 equals P2 V2. That's all that's changing. So it's a Boyle's Law type problem. All right. 2.00 is the number of atmospheres I have. That's my starting pressure. My starting volume is 9.00. Pressure 2 is what I'm looking for. But I'm going to call it PA because I'm going to end up with another pressure called PB. Okay? So P2, we're going to call it PA. And I'm multiplying it by the new volume. Now, what's the new volume going to be? I've got to add these two together. Because remember, the gas is going to flow in such a way that it's filling up both of those containers when the valve opens. So 9 plus 3 gives me 12. And I need to have 2 decimals, 12.00 atmospheres. Okay, now I want to solve for this. PA equals 2.00 times 9.00 divided by 12.00. And I've put that in my calculator already, and I found the answer to 3 significant figures. It's going to be 1.50 ATM. All right, let's draw a line right here, and I'm going to go to the other side. I've still got to do the same thing with this gas. My first pressure, P1 times V1 equals P2 times V2. My first pressure is 3.00 atmospheres. And my first volume is 3.00 liters equals, again, we don't know P2. I'm going to call this PB, not peanut butter. I'm just calling it PB because it's the pressure of container B, multiplied by 3.00 liters. So it's the pressure of the new pressure of gas B. Again, I'm sorry, not 3.00 liters. So I have 3.00 atmospheres times 3.00 liters equals PB times the new volume would be 9 plus 3. Again, that's 12.00 liters. Okay. And PB will be equal to 3.00 times 3.00 divided by 12.00. All right, when I put that in my calculator to the nearest 3 significant figures, I get 0.750 atmospheres. All right. Last thing we need to do, because I wanted to know the pressure of the mixture. I know the partial pressures of my two gases in the mixture. The total pressure, P total, is going to equal PA plus PB. So I need to say 1.50 plus 0.750, and if you add those up, you come up with 2.25 atmospheres. All right. Move on to the next part. Example number 2. 27.4 liters of oxygen gas at 25 degrees Celsius and 1.30 atmospheres and 8.50 liters of helium. Hold on, let's back up. 27.4 liters of oxygen gas. And it's got this temperature, right? And that many atmospheres, got that pressure. And I've got a different gas, so I'm going to switch colors so that I can just stay organized. 8.50 liters of helium gas at 25.0 degrees Celsius and 2.00 atmospheres were pumped into a tank with the volume. So the new tank, it's a new volume, 5.81 liters at 25 degrees Celsius. Now, if I need to use those temperatures, I'll have to convert them over to Kelvin. But let's look at it first. Did the temperature change? 25 degrees Celsius, 25 degrees Celsius, 25 degrees Celsius. No, temperature did not change. So even though I squared it because I thought it was important, I'm going to go back and cross it out. Since it does not change, I'm not even going to use that. It's a constant. It's not needed for this problem. All right, now let's continue. Calculate the new partial pressure of oxygen. So the new partial pressure of oxygen. All right. And what's changing? Pressure and volume. Because I'm going to get a new volume and I want to know what the new pressure is. So we're going to use P1 V1 equals P2 V2. We need to calculate the new pressure of helium. I have P1 V1 equals P2 times V2. I need to calculate the total pressure of both gases. That would be the pressure of O2 plus the pressure of helium, He, equals the total pressure. I need to calculate the mole fraction of oxygen after mixing. So let's just write that over here. The mole fraction, remember mole fraction comes from taking your partial pressure divided by your total pressure. So I'm going to say my pressure of O2 divided by the total pressure equals X of O2. And then finally, down here, I'm going to calculate the mole fraction for helium. That's XHE. And that's going to be equal to the pressure of helium divided by the total pressure. That's kind of my planning stage. So I know how I'm going to solve each part of the problem. Start with the first one. P1V1 equals P2V2 for O2, for oxygen. P1V1 equals P2V2. I'm going to write 1.30, that's my starting pressure, times 27.4. It's my starting volume, the number of liters, equals P2 times my V2, well, the new volume is 5.81 liters. P2 is going to be equal to 1.30 times 27.4 divided by 5.81. So multiply those, divide by that. P2 equals 6.13 atmospheres. And by the way, we could call that P of O2. That's our new pressure of oxygen. We solved the first part. Now we need to do the same thing for helium. P1V1 equals P2V2. For helium, our first pressure is 2.00 atmospheres. Our first volume is 8.50 liters. Second pressure, we don't know. The second volume is 5.81. Let's divide to solve for P2. 2.00 times 8.50 divided by 5.81. P2 equals 2.93 atmospheres. Again, P2 is helium, that is our pressure of He, just to keep it straight. Our total pressure is going to be equal to pressure of O2 plus the pressure of He. So I'm just going to take 6.13 plus 2.93, and I come up with 9.06. It looks like a 4. 9.06 atmospheres. All right, we answered the first 3 parts. Now, let's go on and answer the next part. I'm just going to draw a line there to keep it separate. Let's find the mole fraction. of O2, mole fraction of O2 is going to be our pressure of O2 over our total pressure. In other words, 6.13 over total pressure is 9.06. And that's going to give us 0.677. By the way, if we put our units in there, we would say atmospheres, right? Then down here we would have atmospheres. Those units cancel out. Mole fraction has no units. It is a unitless number. I know that seems contradictory, but when the units cancel out, there is no unit. Okay. So then we have XHE. XHE is the pressure of HE over the total pressure. So we have 2.93 over 9.06. 2.93 over 9.06. When you do that in a calculator, you're going to get 0.323. Again, our units actually cancel out. There's no unit to this number. All right, just a couple more. All right, let's talk about water displacement very briefly. Not a whole lot to this. There's a lot of words, but I'm just going to go through it kind of quickly. The most common use of Dalton's law is water displacement because it's a common way for us to do a lab, a really common way to collect gases and measure their pressure and volume, and the amount of moles of gas that we get is by collecting it over water. The problem is, when you collect something over water, there's inevitably always going to be a little bit of water vapor in your sample, and we don't want to know the pressure of the mixture. We want to know the pressure of just the gas that was produced. So you should read over all this to understand the lab procedure. Basically, we have a reaction in a closed vessel that's connected to a tube that allows the gas to flow through that hose or tube up into an inverted container that is filled with water and submerged in a pan of water of some sort. And as the gas bubbles through here, we collect gas over the top of the water. But it's going to pick up some water molecules. I don't want to know the pressure of just what's in here. I want to know the pressure of the gas that went through this. So we've got to subtract the pressure of water, because our total pressure, just like Dalton's law, total pressure is the pressure of each gas added together. Our total pressure here is the pressure of the gas that's collected plus the pressure of water vapor that was added into that gas. We don't want the water vapor pressure, so we have to get rid of it by subtraction. This means that we need to get the water vapor pressure from somewhere, and that can come from a table. The only thing water vapor pressure depends on is temperature. It doesn't matter how much gas you have. It does not matter it doesn't matter how big your container is. There's a lot of different variables. Really, it only matters what the temperature of the room is, and that will tell you the water vapor pressure. You can't really measure the pressure directly, okay? So what we can do is we can make some assumptions, and they're good assumptions, that the pressure inside the container, because of the way this is set up, the pressure inside the container is going to be equal to the air pressure in the room, okay? So what we're going to do is determine the atmospheric pressure atmospheric pressure in the room, and then we subtract the water vapor pressure from this pressure. Okay, so we find the water vapor pressure in a table, and we subtract that number from the atmospheric pressure in the room. We can also measure the volume of the gas, and when we measure the volume of the gas, we can learn other things like the number of moles that are in the container. All right, we got one practice problem based on this concept that we want to go over real quick. A sample of solid potassium chlorate was heated in a test tube. See the figure above. It was decomposed by the following reaction. It gives us this reaction. The oxygen produced was collected by displacement of water at 22 degrees Celsius and at a total pressure of 754 torr. Okay, we have temperature, we have pressure. The volume of the gas collected was 0.650 liters, and the vapor pressure of the water at 22 degrees Celsius is 21 torr. Now, what's this 21 torr? It's the vapor pressure of water at the given temperature. All right, first thing we need to do is calculate the partial pressure of O2 in the gas collected. So we know the pressure, we know the total pressure, we know the water vapor pressure. We need to find the pressure of oxygen. So part A is just subtraction. The pressure of O2 equals the total pressure minus the pressure of water. So pressure of O2 is 754 torr minus 21 torr. All right, and that is 733 torr. Now this problem is actually a lot more complicated, it comes from an AP problem that has a little bit more involved. I've simplified it a little bit because for our purposes, we don't want to get into something called gas stoichiometry, which is something that the original problem had in it. We'll talk about that later. But right now it just asks us to calculate the mass of O2 collected. So what if I wanted to find the mass? Well, first I have to know how many moles. I know pressure, I know temperature, I know volume, but I don't know the moles. So I've got to figure that out. So for part B, let's get organized with what we know. Our equation is going to be PV equals nRT. All right. And our pressure is given to us in torr, which is the same thing as millimeters of mercury. I want to convert those into atmospheres so I can use the gas law constant. So really, the torr, this 733 torr, for it to be useful to me, I need to convert it into atmospheres. And we know the relationship between atmospheres and torr, 733 torr, or millimeters of mercury. 760 torr is equal to 1 atmosphere. So I want to find that answer to 3 sig figs. It's going to be 0.964. 0.964 atmospheres. Now I can plug it into my equation. So I did that so that I can plug it in down here. Okay. Our pressure, 0.964 atmospheres, times our volume, which is 0.650 liters equals N, that's my unknown, times R, 0.082. We usually say 0.0821, but I believe it is, 0.08206 liter atmospheres per Kelvin mole in R. And then T, my temperature is in degrees Celsius. I need to change that as well. So 22 degrees Celsius plus 273, and that's 295. All right, now I just need to solve for N. So N equals 0.964 times 0.650 divided by, and we got to have this in big brackets, 0.08206 times 295. Make sure you put it in brackets when you put this in a calculator. This is one thing I do want to show you how I put it in, just because a lot of mistakes come from doing this wrong. 0.964 times 0.650. Don't have to worry so much about what's on top if we're just multiplying, but when you divide, start your parentheses, 0.08206 times 295. You got to make sure you have parentheses around everything that's in the denominator. And I get 0.0259. 0.0259. Moles of O2. I didn't really want moles of O2. I want to find grams of O2. So very last step, and then we're done with this video. 0.0259 moles of O2. 1 mole of O2 is equal to 32 grams of O2. And if you're curious how I got that, that's the molar mass. I found it on the periodic table, and I know it with a pretty good amount of certainty. I think it's 2 decimal places that's certain too. So 0.0259 times 32 divided by 1. 0.08288. I want to round to 3 significant figures, so it's 0.829. 0.829 grams of O2. Finally, our final answer for that question. So this one's a bit of a doozy, and it's actually got one additional step in the original problem. We'll learn how to do that type of problem later. I hope this was a helpful review of the gas laws. It's very important that you understand the gas laws as we move on into different things. Soon we're going to be talking about something called gas stoichiometry, and this is really foundational to that.